Good morning. Good morning once again. Welcome to our virtual lecture. Uh, Today we will start chapter 9. I did send out an announcement regarding our lecture today. But first, before we get started, I want to make two announcements. One is regarding the two quizzes due on Thursday. There is a quiz on chapter 8 and chapter 9 due on Thursday midnight. Make sure you complete those two quizzes. We are on the descending here right now. 2 weeks, we will take our final, and I want to prepare you. I want to give you, time to prepare for the exam. So hopefully by weekend, I will have looked at the questions on the final exam, send you the study guide, what you need to have, and if need be, prepare the formula sheet or the constant equation you will need. I will plan to send out by weekend. That way you will prepare yourself ahead of time. Other than that, chapter 8 and chapter 9 they're the same. For those who missed the lecture last Tuesday, this past Tuesday, we finished chapter 8. I could not share the lecture recording because of technical glitch I had with my iPad, and the market could not communicate. And when I restarted it, I may have forgotten to record the lecture. Nevertheless, I expect you to read whatever you missed during that lecture session. Hope everyone is doing good this morning. I know situation is getting worse with respect to COVID-19. Hopefully we will make it safely, and things will be better for on-campus in-person instruction come fall. Other than that, let me share my screen and we will get started right away with our lecture on chemical bonding, molecular geometry, and chemical bonding. All right. Hopefully you are able to see my screen. Can you see my screen? Somebody to use the chat feature and say yes. Last week, I started lecturing while I was on mute. Can you see my screen? Thank you. Stephanie, yes, thank you, I got you. So we are on the same, we are safe to continue with our lecture. You can see my slides and my whiteboard, and then we can get started right away. If you have any question, you can use the chat window at the bottom of your screen, and I'll be able to respond. I'm just gonna keep this. If somebody join us this morning, I will see them on the waiting room. So if you look at the title of chapter 9, it's not something new, especially when we talk about the chemical bonding or bonding theories. We're still revisiting what we covered in chapter 8, and we will extend or use the Lewis structure for molecules and polyatomic ion to predict the molecular geometry of molecules. So we're just gonna be looking at the same molecules we looked at in chapter 8, all right? I'll recommend that go back again, familiarize yourself with the Lewis structure, how to draw the Lewis structure, because that is the foundation of predicting the molecular geometry of a molecule. Um, uh, Today, I will show you a couple of models of atom and see how the molecules, or how we will come up with a conclusion on how the molecule will look like. Just like before, here is the roadmap on the, chapter 9. We will look at molecular shapes, all right? Quite often we think that molecule you can draw any way you want. For example, methane, you may think that they are 90 degrees angle between carbon and hydrogen. That's not how it should look like. There is a powerful model we use to predict the shapes of molecules. In 9.2, we will look at what we call valence shell electron pair repulsion model. This is a powerful model used to predict the shapes of molecules, all right? Remember the rules I gave you in drawing the Lewis structure for molecules. We will also use this one in the same way as those rules to predict the shapes of the molecule, all right? We will look at two types of, geometry, electron domain geometry and molecular geometry, and talk about the polarity, which we need to go back to electronegativity on the periodic table, okay? We just in chapter 8 talked about the, covalent bond, double bond, single bond, and triple bond using lines to represent chemical bonding. We will see now in chapter 9, section 9.4, how the orbitals, all right, overlap to form a chemical bond. If you're bringing hydrogen and bringing carbon to form a chemical bond for CH bond, how does the orbital overlap? We'll look at that, and hybridization, double bond and so forth. And we'll look at 9.8, the atomic molecules with respect to chemical bonding. Let's see. When we talk about the molecular shape, you may think that, for example, H2O, you see quite often maybe your instructor giving you this and say oxygen is bonded to hydrogens in this way, but that is not the, you may think that this is 180. It's not, all right? How do we know that it is, or it assume this shape we call PAN? All right, why do we say that carbon dioxide is linear? All right, using the valence shell electron pair repulsion model, we will see how to come up with a conclusion as to when the molecule is linear, paired, trigonal, planar, all these. You have to commit to your memory all these terms when we say T-shape, okay? So we will use the Lewis structure for molecules. Go back to 8.5, drawing the Lewis structure for molecules, because it's the foundation of predicting the molecular geometry. We will use Lewis structure. Go back again to drawing the Lewis structure. There are rules I gave you. You can synthesize your own rules by reading the relevant section in chapter 8. Now, so when we talk about the shapes here, you see these are, I'm just gonna give you just few, we will look at all these shapes in chapter 9. And to come up with this, we use what we call valence shell electron pair repulsion model. And what determines this is what we call the bond angle. You're gonna memorize the bond angle for each shape. For example, when we say linear, 180, that determines the shape of the molecule. When we say trigonal planar, all right, what are the bond angles? 120. When we say tetrahedral, 109.5. All these determine the shape of the molecule. Octahedral. If you look at the octahedral here, bond angle 190 and 90 versus 90 and 120 for trigonal or power pyramidal and octahedral. These are some of the factors, or one of the factors which determine the shape of the molecule. And then again, the electrons, all right? Electrons around the central atom, if you look at the yellow coded on these shapes given on the slide, the central atom is what is at the center. We look at the electron domains. I'm going to talk about the domain in a few minutes. It determines the shape as well. So bond angle as well as the electron domain determine the shape of the molecule. And we use what we call valence shell electron pair repulsion model to predict the shape. You need to understand what this first for me. Fallen shell electron pair repulsion model. You know what is fallen shell? Fallen shell, the outermost shell, the highest n value when you write the electron configuration, and we say electron repulsion. Electron pair, you know electrons are negatively charged, and if you bring negative and negative, they will what? They will repel. And that influence the shape of the molecule. That repulsion determines the shape of the molecule. Let's see how you look at the domain, or what we mean by domain in molecular shape of molecule. That lone pair, look here, lone pair, and we say pair is 2, all right, double bond, triple bond, all right. All these are counted as a domain. You do not count the electrons as, you know, as a separate domain. In other words, if you look at the domain around the central atom in this generic chemical formula of a molecule, this is a domain. You cannot count these two as two domains. I know it's confusing to some of you that why am I calling this a domain, whereas I'm also calling this a domain instead of saying two domains. You do not see that as two domains, all right? This is a domain. Lone pair is a domain here. This is a domain, this is a domain, this is a domain. And by the way, we use domain with reference to central atom, what is at the center, all right? What is at the center, unless it is, you know, a long chain linear carbon to carbon molecule bonding, we use only the central atom to determine the domain. So we use those around the central atom. In this case, A is our central atom. And when you look at this, 4 electron domains, where are 4 coming from? Somebody might say 1, 2, 3, 4. Is it the 4 lines? No. The 4 electron domains here is the lone pair here is a domain, that is 1. The single bond on the left is 2. The double bond here is another one, and the single bond here is another domain. Therefore, this is where the 4 domains comes in. If I add a triple bond, I'll count that as a domain. Let me just see if I can come up with something with a triple bond. Let's say I have something like this, because that thing exists. So this is a domain right here. This is a domain right here. You look at the regions around the central atom. I can have this. So this has 2 domains. This has 2 domains. I can have ammonia, NH3. The Lewis structure for this will have 2 electrons sitting on top of nitrogen, sorry. So I count this as a domain here. This is 1, 2, 3, and then this is another domain, 4 domains around the central atom. So this has 4 domains. This is critical. Identifying the domains around the central atom is critical in determining the molecular geometry of molecules. So we need to know how to count the number of domains around the central atom. Now, in counting the electron domains around the central atom in Fallon shell electron pair repulsion theory or model, a dash is not included. A. non-bonding pairs of electron, single covalent bond, core electrons of core level of electron pair, double covalent bond, triple covalent bond. Having gone through, the concept of domain, which one is not included? Which one did I not talk about? Let me see what Antonio is giving us. Give it a try again. See, thank you, David. Yes, thank you. It is, Antonio, it is, you don't count the core. What do we mean by core? If you look at the nitrogen, for example, on my, whiteboard here, all right, we don't include the core. Remember, this stands for valence shell electron. We're looking at the valence electron. So what is wrong with A here is when you say non-bonding pair, these are non-bonding pair. Remember what we talked about in chapter 8? We call these non-bonding electrons. And we do count in determining the what? The domains. And that is why in my, bullet point here, lone pair, this is the lone pair sitting on the central atom. Is there any double bond hooked up to the central atom? That is another domain. Is there any triple bond hooked up to or on the central atom? That is another domain. So here, non-bonding pair, Antonio, stands for lone pairs. Maybe I should put here lone pairs for many, depending on how many you have, all right? So the Lewis structure for H2O is, we'll have this. We will see later on. Let me even not give you the shape right now. Let me just use for H2O. If you draw the Lewis structure for H2O, 1, 2, these are the lone pair. So we have 1, 2, 3, 4. These are 4 domains. 4 domains. We count the pairs. All right. The correct answer is C, core level. Here is valence shell. You're looking only at valence electrons. I hope we are on the same page. So pay attention to how you determine the electron domain. That will be one of the key things we need in predicting the molecular geometry of molecules. Now, so what is valence shell electron pair repulsion model? It's a model used to predict the shapes of the molecule. If I had time to go do shopping, I was intending to get the balloons and make these models for you to see. These are some of the shapes you will encounter in molecular geometry for molecules, and the pairs arrangement you see here, it is based on the repulsion of electron. All right, repulsion of electron to minimize, to minimize the repulsion. They assume the shapes you will see. It's just like bringing 2 magnets together, south and south. They don't like each other. They will try to push away, and that is what is happening in the valence shell electron pair repulsion models, to have a linear, to have a trigonal planar, to have tetrahedral, and so forth. So that's what we are going to use to predict the molecular geometry of molecule. There is a table which we will walk through. I think it is 1 page in the text, but in my slide, the table has been broken into each geometry, all right? That table in the text shows electron domain geometry around the central atom. And by the way, just to point out to you, there are 2 types of geometries you will encounter, and you got to read the question when presented. There is what we call electron domain geometry, and then there is molecular what? Molecular geometry. This has abbreviation EG and MG for this molecular geometry. This has to in the first one, electron domain geometry, we look at the electrons around that, how many electrons around, but in molecular geometry, we look at the atoms hooked up to the central. To differentiate that, let me go back to maybe H2O, for example. In electron domain geometry, we look at this. This is what I'm looking for, electron domain geometry, e.g., look at what I'm circling. There is a domain here, there is a domain here, there is a domain here, there is a domain here. So it is 1, 2, 3, 4. There are 4 electron domain. But when I look at the molecular is only this one and this one. How many atoms? When we say molecular geometry around the central atom, you only have to look at the molecules hooked up to the central atom, and I've just walked you how you look at the lone pair, single, double, and triple around the central atom. Now, these are the domains, and there are 6 of them. When we say electron domain geometry, right here, e.g., this is a domain, linear, all right? The point angle between atoms hooked up to the central, it assumes this arrangement for molecular geometry. All right, there is tetrahedral 1, 2, 3, 4. All right, and the point angles, predicted geometry for point angles. These are how you look at the what? The arrangement around the central atom to say electron domain and molecular geometry for atoms. These are 6. You see those 6? Starting from linear, trigonal, planar, tetrahedral, and trigonal, pyramidal, and octahedral. These are the general arrangement for atoms around the central atom. Point angles, all right? 120, 90, and then there is 90, 90 for octahedral, So these are the general molecular geometries. The question now is, how will you predict the shape of the molecule, both electron domain and both molecular geometry? Because a question could ask you, what is electron domain geometry for this? Or what is electron domain, or what is molecular geometry for this? The conclusion has to do with how you come up with the best model using Fallon Shell electron pair repulsion model. And if you look at rule number 1, in using that model, you got to draw the best Lewis structure. So if you didn't do your homework in Lewis structure, please go back again, because it will compound. If you don't know the Lewis structure, you will just, chances are you will miss the point in molecular geometry. And then you determine the electron domains. Remember what we say, double bond is a domain, triple bond is a domain, lone pair is a domain. And then you use that to predict the molecular geometry. There is on page 345 and 348, you will see those geometries. Well, the last, I know you can handle the first one. I know you can handle the second one, right? I know I've walked you through how to draw the Lewis structure last week, or last lecture, not last week. We just went through in section 9.19.2 how to identify the domain, right? Now, 3 here is, I want to give you a set of equation on how to use that to predict the molecular geometry. And this is what I'm just going to, I don't think you'll see in the text. And this is A P X EN, all right? This is a generic formula you can use to help you predict the both electron domain and molecular geometry. Let's define what these stand for. A here, this is the central atom. This is the central atom. And BX subscript X stand for number of atoms attached or hooked up to central atom. How many atoms is hooked up to or attached to central atom? And then En here, E subscript N stand for number of what? Number of lone pairs of on maybe on central atom. How many lone pairs are on central atom? For example, let's see for example on the screen here for ammonia, all right? You are given the chemical formula, or worst even they might give you only the name here. You are expected to know the name. Look at where you can start from. Chapter 2, chemical formula as a name. So if you are given the name, you should translate to chemical formula. And then from chemical formula, you start now from step number 1 to Lewis structure. To predict now, to move from here and predict the geometry of the molecule, we use this formula on my whiteboard. And how does it work? This is what you will do. I'll say, using this, let's see this one. A is nitrogen, so it is a, how many atoms are hooked up to the central? There is nitrogen, hydrogen, hydrogen. So it is P3. Subscript 3, it tells me that I have 3 atoms hooked up to what? To nitrogen. How many lone pairs? Not how many electrons. I say lone pairs. This is counted as a pair. So this is going to be E1. You can leave it just E or E1, that's fine. If you want to go with 1, I'm fine with that. That is the domain or the combination. Well, right here, let me just forward to the next table, which I'll allow you to use. If I look at the domains, I have how many hooked up to 3. So for 3, I'm just gonna come back again to that. If I have 3 atoms hooked up to, you see this 1, 2, 3, this is electron domain. 3 domains. But P3 with no non-bonding pair, you see this? 3 domains, all of them are atoms, and then the shape is trigonal planar. But if I have 2 atoms, bonding domain, that means this stands for how many atoms are hooked up to the what? Hooked up to the central atom, and lone pair. That means lone pair. Number of non-bonding domain, that means stand for pair. Somebody's just saying, are you writing on the whiteboard? No, I'm not writing. Can you see my whiteboard? I'm just on the, I'm just moving my cursor key over the PowerPoint slide. I'm not writing on the whiteboard. I'm not writing on the whiteboard. Thank you. Can you see the whiteboard, please? Somebody was saying that I wasn't writing the whiteboard. I was just moving the cursor key over my PowerPoint slide trying to explain this. Look at the whiteboard, trying to explain the NH3. I was trying to explain this on this domain right here. How did we end up with, you know, trigonal power pyramidal? Oh, somebody saying that they cannot see. Stephanie, you cannot see the whiteboard. I can see the whiteboard and the PowerPoint, but whiteboard is over the PowerPoint slide. Can you, is it okay right now? Is it okay right now? Can you see the PowerPoint slide? Let me just something here, readjust the screen, readjust the screen a little bit and see if we can, we are all on the same page. Right, let's see. Is everything visible right now? Is everything visible right now? Is everything visible? Can you see the PowerPoint slide? Yeah, maybe try leaving and coming back. Everybody, can you see the PowerPoint slide? I just want to make sure that everybody, I can see everything normally. I'll be back the rest of the class. All right, thank you. I hope maybe if you can leave and come back, it could be your end. So thank you. Let's see. This is what I was saying, that how do we end up with this trigonal pyramidal right here? I was explaining how you use this equation. And for ammonia, Stephen, for ammonia, this is the configuration for this molecule from the Lewis structure. This is the configuration AP3, which means 3 hydrogens hooked up to nitrogen, and there is a lone pair. Lone pair, that means E1. There is a pair right there. I had to fast forward to, you know, the configuration for that. Configuration for that is right here. That I have, you know, 3 pairs. Not that, 3 pairs around the central. So if you have 3, look, you have 4 domains. Remember, it was like this. This is what we had. Nitrogen hooked up to hydrogen, hydrogen with the domain there. If you look at the electron domain for this, that means how many electron domain geometry? 1, 2, 3, 4. There are 4 domains. So the 4 domains is tetrahedral. This stands for, on this table, this stands for the domains. I'm just writing how many electron domains. 1, 2, 3, 4. 4 domains. You predict electron domain as tetrahedral. These are the terms you will be asked to predict the domain for, tetrahedral. But the molecular geometry, Mg, how do we know that? It is tetrahedral? If electron domain, I have 3, 1, 2, 3 atoms. You see this bonding? How many atoms are bonded to the central? 3. How many lone pairs? And then this will be trigonal, trigonal what? Trigonal pyramidal. All right, pyramidal. So that is how you use the domain to predict both the molecular. That is why here, let me just go back to where we are right here. How did we say that the electron domain, the molecular geometry here is trigonal pyramidal, trigonal pyramidal? It's based on the equation right here. This is what you'll be using. This is what you'll be using in predicting the shift. Somebody left and came back. Can you see the board? Hopefully somebody can see the board. Aaron, thank you. Hopefully everybody can see the board. So this is how you use this equation to the last term right here. I mean the last, or step number 3, it has to do with understanding how to use this configuration, how to use this configuration to predict the molecular geometry without just trying to read. You know, if you just read the text and you are given an example such as this one, suppose I give you something else, like, you know, why do we say that you may think that, let me just give you, you may think that these two right here, they have the same, all right, they have the same, or even, let me just use something different here. Let's see this SO2 like that, all right. Look at those two molecules on the board, and I'm going to use the rules here, all right? I'm going to use the rules here to show you how powerful it is, how powerful this configuration works, XEN. You may read in the text, this one is linear, and you think that anything with this configuration is linear. No, no. Let's try the first one. For CO2, all right, we draw the Lewis structure for CO2. CO2, let's see. Carbon is bonded to carbon. Remember how we draw the Lewis structure? Carbon is in group 4, and oxygen is in group 6. So this is 12. All right. We have 16 valence electron. I'm drawing the Lewis structure for carbon dioxide. What I'm trying to do is predictive molecular geometry. First, I'm doing the first one, Lewis structure for CO2. Remember what we say, subtract the bonding electron. I've used 4. There is 2 here, and there is 2 there. So remain 12. So each one of them takes 6, 6, 6, 6, 6, and nothing is remaining. So minus 12, 0. Satisfy the octet rule. This will, you'll end up with a double bond on either side of the molecule. This is the Lewis structure for carbon dioxide. 2 here is, this is the best domains Lewis structure. Determine the electron domain around the central atom. This is what we are focusing on. We have 1 to 2 domains. And for 2 domains, it is of this type, A, P, 2. AP2, there is no, we don't have any lone pairs on the central atom. Remember, our geometry has, molecular geometry is based on the central atom. For this valence shell, we paste on the central atom. Therefore, for this, it is AP2. With this one, I'll give you later on, I'm just gonna walk you through this. I'm just going to give you a handout on these domains on table 9.2. If I know the domain, how many domains I have on the central atom, 2 domains, no lone pairs on the central atom, what I box it in blue, and 2 bonding, oxygen and oxygen, and then molecular geometry is linear. We can also have, you know, the same configuration for electron domain as well as the molecular geometry, linear, and that is how you use APN. That is how I'm using this equation or configuration to reconcile with table 9.2. So for this, I'll say electron geometry is linear. And then molecular geometry is linear. It's the same thing, but it's not always the same. Molecular geometry and electron domain geometry is not always the same. It varies from molecule to molecule. So you have seen how to use the three rules and how to use this equation or this configuration to predict. Let's see for sulfur dioxide. For sulfur dioxide, somebody might assume and say it's the same thing. I see, perfectly they look alike. I mean, two oxygen hooked up to something. Why can't they be the same thing? Let's look at what we'll end up with. If I have sulfur dioxide, right? Sulfur dioxide. Sulfur is in group 6. Oxygen is in group 6. I'm drawing the Lewis structure now. Times 2 is 12. This is 18. Valence electron. 18 electrons. Let me just say 18 electrons. So draw the skeleton of the molecule hooked up to oxygen. I've used 4, so subtract 4. This remain 14. Remember, all right? Remember, a single line represent 2 electrons. So the 4 here is coming from the line here, the line there, So octet rule on the external atom except hydrogens. I have 2 there. Let me just put it there. I keep oxygen on this side. Oxygen has 6 here, oxygen has 6 here. So I've used 12 to satisfy octet rule on the external atoms. Remain 2. The 2 goes on the central atom. The 2 goes on the central atom. Not 3, but I meant to say 2 here. There are 2 there. We need to satisfy the octet rule on the central atom by making a double bond. You have to satisfy the octet rule on the central atom. Once you have, all right, once you have past Lewis structure, this is the past Lewis structure for sulfur dioxide. We use the central atom to predict the shape. This is where now A, P, X, E, N comes in. And for this, it is A, P2, and then E1. That means there is a lone pair of electron on the central atom. There is one domain there, there is another domain there, there is another domain there. There are 3 domains. 2 plus 1 is 3. Look at the subscript. 2 plus 1 is 3. That's the domain. What our box is, what I need to do. So if I'm looking for the 3 domains, I'll go to look at these 3 domains. So this is what I'm looking for, 3 domains. And if I'm looking for electron domain geometry, all right, for SO2 sulfur dioxide, I'll say this is trigonal planar, all right, trigonal planar. If I had, right, if there were no central, if there were no lone pairs on the central atom, and then molecular geometry will be trigonal planar, it's the same as that. But in this case, there are 2 atoms and a lone pair on the central atom, and the molecular geometry for sulfur dioxide is panned. It is panned. And if you are asked to draw, this is what you will draw. This is what you will draw. It's just gonna be like this. So sulfur dioxide look like this. Oxygen, no, this is how it look like. Sulfur dioxide does not look as linear with the two pairs, sulfur, and it will look like this, oxygen. Remember, electrons are negatively charged And the lone pairs here will push the two electrons or this domain. It will push the domain. This is a domain, this is a domain. Because there is unshared electron here, it has high electron density to push this shared electron to assume the band shape, all right? But if everything is bound, then we say that that is the shape of the molecule. So you will use this to predict. This tells you the domain. If it was 4, then that's what's gonna be. If we add, that's how you're going to use that. That's how you use the, the last, I wanted to explain the last rule here. Are you going to use the bonding or the bonded atoms to determine the molecular geometry? Table 9.2. And in the exam or in the homework, all right, I don't think in the text you'll have these. Look at my whiteboard. I don't think you'll have this illustration. This will really simplify your work in your homework. That anything on the molecular geometry, anything on electron domain geometry, you have to use this configuration on my whiteboard, especially to explain what is going on with rule number 3. Rule number 3 here. How do you use table 9.2 to predict the molecular geometry? Draw the Lewis structure, whether it is polyatomic ion or neutral molecules. You still have to draw the Lewis structure, narrow it to the central atom, and use the domain to predict how many domains you have. And remember, there are two geometries: electron domain geometry and molecular geometry. It's the same. They are not the same. They are not the same. So clearly, sulfur dioxide has molecular geometry is pent, whereas for carbon dioxide, all right, for carbon dioxide, we have molecular geometry as linear, and they look alike. But unless you draw the Lewis structure and use that configuration, you won't be able to predict. Don't just guess and say it's just gonna work. And that is all what I want to tell you as far as using that configuration. There is something I posted online, all right? There is something I posted online. Let me see if I can pull that. I have this table right here, which you can use. Can you see that? This is what you can use in the homework assignment, in the quiz, so that you know what you are looking for. This stands for the domains. Might not be clear, but I do apologize. I was trying to make a copy and the Xerox couldn't really come out well. The point angle, what you see here is the electron domain, and this is the molecular geometry. If you can, look at the table 9.2, it's fine, but I summarize here and added something you cannot see here, but this stands for AP2, where A stands for the central atom. This stands for the lone pair. If you have no lone pair, you don't see it. If you have no E, that means you don't see it. But if you have E, it's gonna tell you the domain for each. All right, for each. You can also supplement this, and I'll allow you to use in the quiz and exam, so that at least you can predict the shape of the molecule, all right? So I've walked you through how we ended up with that domain, all right? So when we say linear, two atoms hooked up to the central, the molecular geometry, and that's why I've underlined here, molecular geometry. I may ask you the electron domain geometry. You see this? Electron domain geometry and the molecular geometries. You can be asked two questions. What is the electron domain geometry? What is the molecular geometry? So in the text, I'm gonna use this column for the electron domain geometry. And this is the molecular geometry. And this is the domain around the central atom. It's cut, as we go along, it will get more and more. So here is another example. The molecular geometry of CS2 is what? Unless you draw the Lewis structure for this, you won't be able to predict, and let's all work together. So CS2, let's see. CS2 here. Carbon is in group 4, so 4 valence electrons. Sulfur is in group 6, so 6 times 2 is 12, and this is 16. Did I miss something? Carbon is in 4. Sulfur is in group 6A. You add up, give you 16. And carbon is a central atom, so sulfur and sulfur. All right, and we subtract 4 bonding electrons. These are bonding electrons on the Lewis structure, remain 12. All right, so if I have this, I have that, I've used 12, nothing remain. Clearly, this I need to make a double bond on either side. All right, I need to make a double bond on either side to satisfy the octet rule on the central atom. Now, in my configuration, or predicting that I'm gonna look at the central atom, and it assume AP2. So if I am doing a homework, or I'm just gonna come here and say which one gives me AP2, and AP2 is linear, so I'm just gonna say that this will be linear. I don't see lone pairs, so the configuration here helps you in determining the molecular geometry, or without necessarily memorizing for linear 2 domains, no lone pairs. You see, no lone pairs, so we say it's linear. It's not necessarily only CO2. That's what you need to do for A. I mean, the correct answer is A for this. Any question on this slide? Any question? The author doesn't give you that generic formula, doesn't give you this right here, but I see it's working. It's gonna simplify your work. So if you have 3 domains, all right, if you have 3 domains, they are, all right, this is electron domain. It is trigonal planar. But when it comes to molecular geometry, you can either have trigonal planar or a pen. In trigonal planar, that means 3 atoms are hooked up to the central atom, and there are no lone pairs on this. You can have 2 atoms hooked up to the central atom, and there is a lone pair, such as sulfur dioxide. It will just come out clearly. Nitrate, no, nitrite, this is nitrite. ITE, there is a domain here, there is a domain here, there is a domain here. If I was to use, on the example here, if I was to use this one, the last one here, if I was to use my configuration, it looked like this. A is nitrogen, the central atom. B2, that is 2 oxygens hooked up to it, to the central atom. And then it is E1, there is 1 lone pair. So my handout, what is AP2E1. If I'm looking for electron geometry, it is trigonal planar. If I'm looking for molecular geometry, it is pan or V-shape. Some others call it V-shape, but it is pan. So that's how you use this configuration, AP1. It will help you in. And this applies to other domains. Let's see for sulfur, molecular geometry for sulfur difluoride, sulfur difluoride. Sulfur is in groups, group 6. Fluorine is in group 7, so 14. I'm multiplying it by 2. I end up with what? This is 20, right? Sulfur group 6. Fluorine is in group 7 times 214 when I add is 20. Let's see what's gonna happen here. When you draw the skeleton, the molecule, I've used 4, remain what, 16. I've used 4, there are 2 electrons here, there are 2 electrons there. So minus 12, I'm using the 12 here to satisfy the octet rule on each of the what? Each of the fluorine. Sulfur does not satisfy the octet rule. And we need to, let's see, 12. Remain what? Remain 4, right? Remain 4. The 2 goes on the central atom. Let's see if we have 21, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 electrons, yes. Does sulfur satisfy the octet rule? 1, 2, 3, 4. Yes, it satisfies the octet rule. Each of the atoms satisfies the octet rule. So the next now is to zoom into our central atom. And it is of this form, A, P2, E2. There are 4 domains. So for 4 domains, these are 4 domains. There are 2 atoms hooked up to the central atom. I'll come back to that, Natalie. There are 2 atoms hooked up to the central atom, that is fluorine and fluorine, and there are 2 lone pairs. These are the 2 lone pairs on my, and this is paired shape. This is a paired shape for this. It is P. It is P. Now, Sanchez, where 12 is coming from, maybe I was fast. You know how we ended up with 20 coming from sulfur and 2 fluorine. We are up that at 20. Subtract the bonding, 2 electrons, 2 electrons. So when I subtract, I remain 16. Initially, before I do that, 12 is the electron I've used to satisfy the octet rule on each of the fluorine. I'm using 6 here, and I'm using 6 on the right side. Fluorine on the right side, fluorine on the left side of sulfur. The total 12 here is the number of electrons used to satisfy octet rule on each of the fluorine. So I subtract 12, 6 from each of the fluorine. Is that clear? Yes. So that was you know, the concept of Lewis structure. And if I see now this domain, we say this is paired right here. And be careful if you are asked, is it electron domain or molecular? If I go back to the handout, which is available online, I will look at the 4 domains. For 4 domains, all right, AP2, E2, for electron domain geometry, it is tetrahedral. For molecular geometry, it is paired. And on the PowerPoint slide, if I fast forward on the PowerPoint slide, for 4 domains, electron domain geometry is tetrahedral, but the molecular geometry is, you know, paired. It's paired. You know, if you try to read just off the table, it will be confusing, and you will end up, you know, memorizing things which it will not help you in the exam. For example, you may think that I'll help you with H2O, and you say, all right, this is what it is. If you look at the T shape, it is because of the lone pairs, all right? Lone pairs of electron repelling the shared electron right here. Electron pair repulsion, they repel. So one thing I want to point out is any, all right, any molecule, any polyatomic ion which will assume this configuration here, if you will draw it just the way you draw this. This is just giving you an example. So I can draw even, I will have to draw pen shape. This is what I'll draw now, the S2, that is gonna be S, and you just have to show that the fluorine is right there, and you'll have your 2 electrons right there. That is what they expect you now, that having walked you through this, what is the molecular shape? This is the shape, that's how it look like. And while still on H2O, in the lab, if you have to come in or in the future, somebody might ask you to make models. All right, there's models. You may have done this exercise in into chemistry, that if you can see, this is my water molecule, and a single line represent a bond, and the white sphere represent hydrogen. The red one, chemistry uses this for oxygen, with the 2 holes representing valence. You know, when you draw for oxygen, dot symbol for oxygen, 1, 2, 3, 4, 5, 6. There are 2 unshared electrons on the models. You will see 2 holes representing valence electron. For hydrogen, there is 1 dot, which means the dot is available for bonding. So if I'm to build a model, all right, if I'm to build a model, you may not see, this is how it look like. You know, it may not, can you see that? Can you see that? Somebody say yes or no. I'm just trying to, show you what the molecule look like. This is the molecular model based on. Oh, you cannot see, somebody say, can you see that? Maybe I need to have white background or green background. Somebody say that it might help. Let me see. Green background might help. Can you see that now? It might be help you. I was just building a molecule right here. I was just building a molecule. See, you can have that. That's fine. So nevertheless, that's what you need to know in terms of. So if you are to draw the same thing for this, you have to molecule. You have to look at the central atom. Silicon hooked up to 2 hydrogens. It's gonna have chlorine. It's gonna have chlorine. It's gonna have hydrogen. This will be tetrahedral. Try this, and you'll see tetrahedral assumption. What I want you to do is, I've just walked you through. It's about practicing. Until you get it. That am I really getting it right? You need to practice until you get it. Let's see this real quick. Hydronium ion. Hydrogen is in group 1, so this means 3 of them. Oxygen is in group 6, so if I add that, that will be 9. Remember what we say with the overall positive, or overall positive means we are less, so we have 8 electrons to work with. You subtract 1. So if we are to do the skeleton of the molecule, oxygen is bonded to, just assume that, bonded to what? 3 hydrogens. And we add 8 minus 6. Where is 6 coming from? The bonding right here. 1 bond, 1 bond, 1 bond. So it's gonna be what? It's gonna be 2. I'll give it to what? Give it to hydrogen. Oxygen goes to central. You don't give what? You don't give hydrogen. It doesn't, it's just 5 octet rule. I mean 2. So, central atom. The configuration is A, P, 3, E1. And this is 4 domains. You add up that. For 4 domains, we are looking for molecular geometry. It is not, you may think that for 4 domains, it is tetrahedral. There is, let me just go here, for 4 domains, electron domain geometry is tetrahedral, but it is 3 atoms bonded to the center, and there is lone pair on the central atom. The molecular geometry in this is trigonal what? trigonal pyramidal. Yeah, trigonal pyramidal. But if I was looking for electron domain, and then I'm just gonna go with that. So that just marked the end of that. All right. You can do the same thing for non-bonding. Any question? This is just explaining what happened with the non-bonding that, you know, the electron domain will tend to push the electron because electron cloud is greater here and they tend to push these single bond electrons or electron in single bonds. They are not as many as electron in the double bond. Therefore, they push this electron to assume this shape. Read on that, all right? Now, let's see what will happen when you have expanded octet rule. Expanded octet rule arises when you have, you know, central atom being element in period 3 and below. Element in period 3 and below, they can accommodate more than 8 electrons. Therefore, this is where trigonal power pyramidal and you know, octahedrals comes in. Because of that, I know we have been trying to say, oh, octet rule. All right, the central atom is, you know, when you look at this expanded octet rule, in some cases, all right, for example, phosphorus pentafluoride. Phosphorus is in row 3. If you draw the Lewis structure for this, all right, you look up what? 1, 2, 3, 4, 5. 5 fluorines on the central atom, right? You may wonder, how comes that I'm violating octet rule for phosphorus? I thought it was just, you know, hey, no. Because of what? Because of the expanded octet rule, they make use of the 3D sublabel to accommodate extra electron coming from, you know, for bonding in phosphorus and any element beyond that. This is where the trigonal power pyramidal will comes in. Don't worry about, you know, don't worry about just trying to keep track of, you know, memorizing trigonal power pyramidal or octahedral for 6. Just draw the way you draw. For example, the one I just gave you, let's just use the phosphorus trifluoride. Let's just use this and see how you will end up with the molecular geometry 5 right there. I'm just gonna say that this is what? Phosphorus is in group 5. Phosphorus is in 5, right? Fluorine is in 7, and 7 times 5 is 35. This is 35. I end up with what? 40. So if you draw the skeleton of the molecule, it is bonded for fluorine, 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 and fluorine. How many have I used? 1, 2, 3, 4, 5. I've used 10. I've used 10 for bonding. What I'm doing is to lose the structure for this. I've used 10 electron out of the total 40. 5 times 7 is 35. 5, that's subtract 10. Now, this remains 30. What I want to do is satisfy the octet rule on each of what? I'm using 6 here. I'm using 6 there. I'm using 6 there. I'm using 6 there. I'm using 6 there. And I've used 30. Nothing remain. 0 remain. If anything remains, just put it on the central atom. If you follow the rules, you know, like, you know, whatever remains, put it on the central atom in this section. So right now, I have nothing to put on the central atom. And using that configuration, it is of this AP5. AP5. And AP5, if you go to domain, 5 domains, AP5, lone pair of electrons, all right? This is AP5, and this is the shape. It is molecular geometry is trigonal power pyramidal. And then trigonal power pyramidal using the handout right here, or in the PowerPoint slide right here. If we go to the table, 5 domains, 1, 2, 3, 4, 5. 5 domains, no lone pairs on the central atom. Then the molecular geometry is trigonal power pyramidal. And then the electron domain geometry is trigonal power pyramidal. There are some cases where you may have 4 atoms hooked up to the central atom and you have what? Lone pair. And then it's going to be seesaw. If you have 3 atoms hooked up to the central atom and 2 lone pairs, and then you say it's this shape, such as this. If you have 2, right? If you have 2 atoms hooked up to the central atom and you end up with 3 lone pairs sitting on the central atom, and then your molecular geometry is linear, and the the electron domain geometry is trigonal power pyramidal. That's how you reconcile these formula I just gave you and electron domain geometry. Because of time, I don't want to, it's the same came with the trigonal power pyramidal. Try on your own, the rest is the same thing, that how many are on the central atom. The one I gave you here is to give you an idea. You can do this and use this table to predict, okay? Read on this, use this table to answer this question that follows up with that, all right? Any question on molecular geometries? Any question? Will you be allowed to use this table in the exam or quiz? Yes. Will you be allowed? Yes, I'll give you this table right here. It's available online. Because you don't have, I'll give you this, just like the solubility table, just like the periodic table. Know how to use this. I've walked you through. Your job is to draw the Lewis structure. Look at the central atom, predict the molecular geometry, predict either electron domain geometry. Sometimes you may be asked both. Any question? I'll allow you to use that table. Practice with it. Look at the worked example, make sure you are getting what is given out there. Sometimes you may try and mess it up. Well, for linear molecules, if it is a linear molecules, the geometry is based on individual atoms, such as CH3, CH2, all right? I wouldn't spend time on that. I want you to pay attention to molecules. When it comes to molecular shape and molecular geometry and molecularity and polarity, is just going back to the electronegativity concept. In order to predict whether the molecule is polar or non-polar, all right, you ask yourself these questions right here, and with respect to the shape of the molecule, you will have to use the electronegativity trend on the periodic table. Remember, CO2, it is molecular geometry, it is linear. With this, oxygen is more electronegative, so it's gonna pull electron in that side, it's gonna pull electron in that side, and the net is 0. There is equal force pulling in equal direction. Net is 0. That means net displacement of electron is 0. We say non-polar molecule. It is important to know the polarity of a molecule. in the sense that when you get to organic, you know the rule of solubility: like dissolve like, polar solvent dissolve polar solute, non-polar solvent dissolve non-polar solute, and so forth. And how will you know the polarity of the solvent? Is when you look at the molecule. This is non-polar. For H2O, we looked at the configuration. For H2O, this is how it look like. Oxygen is more electronegative than hydrogen, and the net displacement of electron is in that direction. We say that this is a molecule, polar molecule, because of the displacement. All right, the displacement of electron. So unless you draw the Lewis structure, look at the electronegativity of atoms, there's no way you can make a conclusion that this is polar or non-polar, unless you see the molecular geometry, use electron. Point to remember is, when predicting the polarity, remember, presence of polar bond does not make it the molecule polar. If you have a polar bond, does not mean the molecule is polar. For example, this is a polar bond because electron is displaced in this direction towards oxygen, but the net overall make the molecule non-polar. You need to pay attention on the displacement of electron. Displacement of electron. That's what I'll be looking at. In terms of polar and non-polar. Now, let's shift gears now to overlap and molecular bonding theory we call valence shell, and there is valence shell bond theory, and there is molecular bond theory. We will see these two types of theories. And when we say a theory, it's not something we can see, we assume that is what's happening. In valence shell bond theory, it's assumed that when a bond is formed, there is overlap of the orbitals of each respective atom. Overlap in the sense that if hydrogen you see on that, there is an overlap, and the sharing of electron will look like this. For hydrogen, two hydrogens, each contributing electrons to be shared, all right? Each contributing to be electron to be shared. We'll assume this configuration in terms of overlap. When you see the overlap right here, this is an overlap of S and S overlap. For S and P overlap, such as in chlorine, the shared electron will be on this portion. Let me just, if we have hydrogen and chlorine, this is the shared electron. This is shared electrons, and the sharing has to do with the overlapping of S and P electron. The space right here represent what we call covalent bonding. So initially, in Lewis's structure, we only draw a line, right? Remember, I was just saying that this is a bond, and we just assume that it's a bond. We say that this is a double bond, right? And triple bond and so forth, but we didn't really look at it. How is the single bond? How is single form formed? How is it formed? How are the electrons being shared? With the valence bond theory, it's the shared electrons is in between, and there is an overlap. of electron. Where you'll see as P or D or you know, whatever it's talking on orbitals is which subshell are those shared electron being shared. If it is in D, then we're going to talk about D. If it is in F, it's going to talk about F. But in this case, we talk about S and S overlap. Understand what is meant by overlap right there to form a bond. This slide, I don't want you to, I don't want you to just go ahead and memorize the numbers seen here. What I want you to understand in this slide is what we call the pond length. It is the optimum distance where there is, all right, where there is a minimum energy required, all right? Minimum energy required to keep two atoms or two or more atoms in such a way that they form a covalent bond. For example, in hydrogen gas diatomic, for hydrogen nucleus electron, the hydrogens you see here is electrons outside the nucleus, electron outside the nucleus. Each nucleus will attract electron from the opposite atom, and that leads to what we call the pond length. In this case, measured in angstrom, okay? And if they are far apart, there's no form pond, but the optimum distance between two atoms, we call it pond length, and it represents the length from nucleus to nucleus, pond length for that attraction to. Now, this is 5.5. There's a term here, hybrid orbitals. What does hybrid means? When we say hybrid, stands for mixing of orbitals. We just looked at how to predict the shape using valence shell electron pair repulsion models. But how does it really fit? All right. To talk about hybrid orbitals right here, hybrid mean mixing. You know hybrid cars? Some of you are into auto. When we say hybrid, you have seen Toyota hybrid. What does hybrid means? Before I relate to hybrid orbitals, let me sidetrack to hybrid. Toyota Prius, it's an hybrid. That means it uses gasoline and it uses what? Electric. Both versus, you know, pure electric versus pure gasoline car. When they say hybrid, it means it can use both. You know, the first time I used hybrid car, I didn't know about it. You know, when you stop at the stoplight, it cut off and it uses electricity. You can't hear anything. Electrons just flowing from the, you know, from the battery. If you're driving at 15 miles per hour, maybe you are using electricity. You are not using gasoline. But when you go past maybe 60 miles per hour, electric or gasoline engine kicks in and you use gasoline. That's hybrid. What I want you to understand when we say hybrid here is the mixing of orbitals in such a way that you can make a bond. For example, let's see CH4. If I draw the Lewis structure, or no, electron configuration, and by the way, we will focus on our orbital filling diagram. This is 2s2, and then 2p6. I should have this to give you a sense of what is hybrid. 2p6 right here, 2p, and then we have 3 orbitals. When we get to 3s, you know, we have 3s right there. And then we have 3p right there. I want you to get used to this 3p, and then you go to 4s, and then you go to 4d. So if we write electron configuration for what? For carbon, which is number 3, 4, 5, 6. All right. So if I draw the orbital filling diagram, 1, 2, 3, 4. Remember, you fill the lower first. Degenerate are singly occupied first before you start pairing. These are degenerate, so it's gonna be right here. They are degenerate. So what I'll do is 1, 2, 3, 4, 5, 6. Those are the 6. All right. Those are the 6 electron or electron configuration orbital. It's not, you know, if I have 4 carbons, right here, each one of them has, you know, each one of them has a single electron. How will it form a bond? How will it form a bond with 1 carbon, yet only carbon has 2 electrons to form a bond? If we bond this, how will it happen? How will the chemical bond happen? This is where the hybrid orbitals come in. You have to generate hybrid orbitals. And this valence, outermost shell and hybrid, we're not gonna use the 2s or the 1s. No, it's the valence shell. Valence shell consists of 2s and the 2p. Remember, N stands for outermost energy level. So in this case, we have to do something with this outermost shell, valence shell right here, in order to do what? To generate orbitals which can accommodate these 3 electrons. We do what we call hybrid. In this case, this is what you will do. You will promote 1 electron, you will take 1 electron and set it over here, and this will be now hybrid orbitals. It's not even 2s, it's not even 2p. It's just gonna be 1, 2, 3, 4, 1, 2, 3, 4. I've mixed the 2s and the 2p, and the 1 electron is there. There's another electron right there. There's another electron right there. There's another electron. I promoted 1 electron into that. We call these hybrid. These are now hybrid what? Hybrid orbitals. Hybrid orbitals. Just to give you what this term means, hybrid. It's the mixing of orbitals in such a way that electrons are available in those hybrid orbitals to form a chemical bond. So with the, if I designate now the lone pairs of electron in oxygen, this will, in hydrogen, they will form pair. This is where the 4 hydrogens form a bond in CH4. Otherwise, if I don't do hybridization here, there is no way I will end up with a CH4 or methane. You got to do what? You have to do hybridization on the central atom. We call this, I took 1s and I took 3 of the, I took 3 of the what? I took 3 of the p orbitals. Don't worry about, you know, how many you took. There is a 1s in these hybrid orbitals right here. I have 1s and I have 3p. We say sp3 hybridization for this to form the chemical bond. That is what is meant by hybrid orbitals. You generate hybrid orbitals in order to form the chemical bond. For H2O, somebody say, let's use H2O here. If you look at the electron configuration, all right, electron configuration for H2O, oxygen electron configuration 2p. You'll have to add electrons to form degenerate orbitals. Hybridization, we mix the way I did here. We're just gonna mix the 2s and the 3p. We say 3 The process of doing this is said to be hybridization, mixing of the orbital. What I did here with the yellow is hybridization of S and P to end up with a degenerate. Degenerate means having the same one, same energy. An electron can occupy those without any without having different energy. Now, beryllium sp hybridization, for example, in the formation of sp3, if you look at this for beryllium, for example, beryllium fluoride, for example, how will beryllium form a chemical bond with fluorines if all the electrons are paired? Remember, beryllium has 4 electrons, atomic number 4. Electron configuration is this. So what we need to do is promote 1 electron to a p. And these are the hybrid orbitals. We call these S and P. We are taking 1 S and we are taking 1 P. We say SP, SP. What determines the sp3 is how many are those available. We cannot say sp3 because we didn't take 3 of them. But in my example on the whiteboard, look at my whiteboard, I had to take 3 of them. Once I promoted 1 electron here, I'll use 3 of the P, which we call now sp3. I'm mixing 3 of them, but here we are only taking a 1s and then 1p, we say sp. That is sp3 hybridization, sp3 hybridization. This applies to, any other sp3. You have to draw electron configuration and see how many. And this hybridization is on the central atom. It's not about, hybridizing the external atom. Hybridization is on the central atom. Well, beryllium trifluoride, for example, here, the sp. Trying to look at hybridization using the illustration on the PowerPoint slide may not be clear. I recommend using the orbital filling diagram because you can see the electrons being promoted to an empty orbital, and you can count how many you have used in order to determine the hybridization. So if we talk about the sp hybridization, boron, maybe somebody is using, let me just see how we end up with sp hybridization for sulfur in sulfur dioxide, sulfur trioxide, sulfur trioxide. Sulfur, 1s, 2s, 1, 2, 3. This is 2p. Sulfur is in group 16, right? So this is 3s, or I shall put here 3s. And then this is 3p right here. Let's see what they mean by hybridization. This is 3p. I'm trying to write electron configuration of sulfur, not silicon, sulfur number 16. So if I do the electron configuration, this is 1. Let me see how many time I got. Yeah, 5 minutes. This will be it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. 16. And we need, all right, we need 3 oxygens to accommodate that. If I look at the 4s, remember there is another 4s right there. It's empty. You know, the next one is 3D. 1, 2, 3, 4, 5. There are 5 of them. I'm just showing you 3D. If I look at the oxygen, I only have what? I only have 2 unpaired electrons right here. Yet 3 oxygens need to be bonded to sulfur. Or will I end up with lone pairs of 3 electrons on sulfur to form the chemical bond with 3 oxygens? It's by promoting 1 electron here. If I take this 1 electron and promote it to here. So I see now sulfur has, all right, sulfur has 3 unshared electrons. We can form 3 bonds with 3 oxygens. This means these are my, all right, these are my hybrid orbitals. All right, these are my hybrid orbitals. Is sp. I'm using 2 of the hybridization. I hybrid mix the 2s, and I mean the s in the 4, and the 2 in 3 p orbitals right here. The orbitals in s, 4s, and 4b, they are mixed together to be available for bonding with oxygen, sp, uh, sp3, 3 p orbitals, and 1s, sp3 hybridization for chlorine, for sulfur on the central atom. You look at how many are available for bonding. So before that, we had what? We only had the 3p unpaired, yet we needed the 3 there. So hybridization will be sp3. Of course, there will be lone pairs here, which will account for the empty shells in there. Because of time factor, I will pick up from here on Tuesday. I'll pick up from here on Thursday. Hopefully we will get started with 10. I want to stop here. Please read on our hybridization. The class is ended. If there is no question, I will stop sharing the screen. Thank you for tuning in this morning. I'll see you on Thursday. All right. Make sure you read chapter 10, start reading chapter 10. We'll finish 9 on Thursday. Otherwise, stay safe and healthy. The class is dismissed. Thank you.